Welcome to Course 2.1, and welcome to the beginning of External Course 2. This program is a specialized training pathway focused on digital modeling of both buildings and construction materials across different scales. Unlike other activities within Exploit 4 InnoMat, which emphasize experimental validation and pilot line development, External Course 2 concentrates on the prediction and design of materials and buildings in digital environments before they are implemented in practice. In this first module, Introduction to Digital Modeling of Construction Materials and Their Properties, you will learn how materials are characterized and how their key physical and environmental properties are translated into structured digital datasets. These datasets form the basis for accurate modeling, sustainability assessment, and performance-based decision-making. You will also be introduced to life cycle assessment and environmental product declarations, which provide transparent and comparable information about the environmental impacts of construction products. This module establishes the foundation for the more advanced modeling techniques explored in the following courses, including energy modeling, interoperability, and multiscale simulations. Thank you for joining External Course 2. Let's begin. In today's construction sector, sustainability, digitalization, and material expertise have become essential competencies. This course has been developed to give you a clear and practical introduction to these themes and to show how they come together within modern digital workflows. By the end of this training, you will understand the fundamentals of green building, the principles behind material characterization, and the basics of building life cycle assessment. You will also see how these concepts integrate into BIM environments and support data-driven decision-making. Throughout the course, you will progressively explore 4 key areas: what green building means in today's context, and why it plays a central role in shaping design strategies; which material properties are required for accurate digital modeling and simulation; how sustainability assessments, including life cycle assessment, are performed in construction; and which digital tools and databases support this work, including an introductory overview of platforms such as One-Click LCA. This foundational knowledge will prepare you for the more advanced modeling techniques introduced in the following modules. This course is fully online and self-paced. It consists of short pre-recorded video lectures and complementary reading materials. You can move through the content at your own pace and return to any section whenever you need. Each module includes a short video explanation and supporting reading material. Make sure to download or view the reference documents linked in each section. All modules are designed to be concise and easy to follow. This course is supported by a range of technical documents and resources that ensure all concepts are aligned with international standards and best practices. You will see references to green building and sustainability frameworks, as well as material characterization standards such as ISO, EN, and ASHRAE, which guide the definition of thermal, mechanical, and moisture-related properties. For the environmental component, the course draws on life cycle assessment methodologies and the principles behind environmental product declarations, including standards such as ISO 14040, ISO 14044, and EN 15804. You will also be introduced to digital tools and databases that support material evaluation and illustrate how data integrates into modeling workflows. You will find a list of technical documents and regulatory references, downloadable materials, technical references, and links to external resources to support your learning throughout the course. Thank you for joining this introduction. You now have a clear overview of the topics we will explore and how the learning experience is structured. Let's move on to the first module of the course, where we will begin working with the core concepts and resources that will guide your learning. I hope you enjoy the course. Introduction to Green Building and Material Characterization for AECO Digital Management. In this module, we will explore what green building really means, why sustainability is a priority in today's construction sector, and why material characterization plays a fundamental role in digital building management. A green building is a building designed, constructed and operated to reduce negative environmental impacts while improving the health and comfort of occupants. The concept, green building, describes both the physical characteristics of a building and the processes applied to ensure environmental responsibility and resource efficiency from early planning through design, construction, operation, maintenance, refurbishment, and eventual deconstruction. This concept is closely linked to sustainability, energy efficiency, and responsible use of resources across the building's life cycle. We are facing a global environmental crisis marked by climate change, biodiversity loss, pollution, and the overuse of natural resources. The built environment plays a major role in this challenge. Buildings account for around 40% of energy-related co-emissions, half of all extracted materials, 1/3 of global water use, and over 1/3 of total waste generation. These impacts will intensify as the world's population grows and global floor area is expected to double by 2060. Because of this, the building sector must take a leading role in the transition toward a low-carbon, resilient future. Sustainable built environments are not only essential for climate action, they also support healthier communities and long-term economic development. According to the World Green Building Council, the future of sustainable built environments is shaped by 4 key impact areas: climate action, resource efficiency and circularity, sustainable finance and ESG, and health, equity and resilience. This holistic approach integrates both environmental and socio-economic priorities and should guide every stage of a building's life cycle, from material sourcing and design to construction, operation, and end of life. In practice, sustainability in buildings means balancing environmental protection, social well-being, and economic viability. It involves minimizing emissions, reducing energy demand, selecting high-performance materials, and designing buildings that remain efficient and resilient throughout their lifespan. In Europe, the concept of nearly zero-energy buildings, often referred to as NZEB, is defined by the Energy Performance of Buildings Directive. Member states must set minimum requirements for energy performance. For example, in Spain these requirements are defined in the Código Técnico de la Edificación 2019 update and in the RIGHT regulation for building services. A nearly zero-energy building consists of a building with very high energy performance and a nearly zero or very low amount of energy required, which should be largely covered by energy from renewable sources, including renewable energy produced on-site or nearby. Therefore, nearly zero-energy buildings typically combine very low energy demand with a high share of renewable energy sources. Buildings are a major contributor to global greenhouse gas emissions, making the construction and operation of the built environment a key factor in addressing climate change. This carbon footprint includes operational emissions, energy used for heating, cooling, lighting, and electricity throughout the building's life. Embodied emissions, emissions generated during the extraction, production, transportation, and disposal of construction materials. Reducing both operational and embodied emissions is essential to achieve international climate goals. By understanding and managing these emissions, architects, engineers, and building managers can design more sustainable, resilient, and energy-efficient structures that contribute meaningfully to global decarbonization efforts. For professionals in architecture, engineering, construction, and operation, AECO, sustainability is no longer optional. Regulations, client expectations, and climate commitments are creating a demand for buildings that are energy efficient, low carbon, and well documented in terms of performance and material properties. This European Commission website provides information on the Energy Performance of Buildings Directive. The EU, under the revised EPBD, is now raising the bar from 2028 for public buildings and 2030 for all other new buildings. The standard shifts towards zero-emission buildings, ZEBs. These ZEBs must not only minimize energy demand, but also generate energy from renewable sources, avoiding on-site emissions from fossil fuels. Importantly, ZEBs are designed to support the energy grid. They can contribute with distributed renewable generation, storage, demand response, and smart charging, enhancing flexibility. Furthermore, the revised EPBD also pushes for deep renovation of existing buildings, so that they too evolve towards zero-emission standards over time. In short, this EU policy reflects a long-term vision. By combining energy efficiency, renewables, and smart technologies, the building sector must align with Europe's goal of climate neutrality by 2050. The Intergovernmental Panel on Climate Change, IPCC, is the leading international body that assesses the science of climate change, its impacts, and strategies for mitigating its effects. Its reports are widely recognized as the most authoritative source of evidence, and they directly inform global policy, from UN climate negotiations to national sustainability strategies. For the building sector, IPCC findings are particularly relevant. They stress the urgent need for low-carbon building design, efficient use of materials, and integration of renewable energy. Essentially, the IPCC tells us that every decision in construction, whether choosing materials, designing energy systems, or retrofitting existing buildings, has a real impact on our climate goals. The IPCC reports are publicly accessible, offering data, recommendations, and tools that can guide architects, engineers, policymakers, and developers in making buildings more sustainable. You can explore the latest assessments directly through the link on this slide. Global ABC, the Global Alliance for Buildings and Construction, is an international platform led by the UN Environment Programme, UNEP, bringing together governments, the private sector, civil society, and international organizations to transform the construction sector towards zero emissions, greater efficiency, and climate resilience. Global ABC's main goal is to raise climate ambition by promoting policies that improve energy efficiency, retrofit existing buildings, and direct new investments towards sustainable construction. The Alliance also tracks progress through its annual reports and tools like the Global Building Climate Tracker, allowing us to measure advancements in decarbonizing the built environment. Finally, Global ABC supports countries in developing roadmaps for building sector decarbonization, offering guidance tailored to national and regional contexts. Visiting their website provides valuable resources, including reports, policy guides, and practical tools.
The World Green Building Council, or World GBC, is a powerful global network that connects national green building councils and stakeholders across the building and construction sector. Their mission is to transform the built environment so that buildings, cities, and communities are resilient, decarbonized, and equitable. World GBC works at local, regional, and global levels. Their strategy focuses on four main impact areas. 1. Climate action, aiming to decarbonize the built environment across the whole life cycle of buildings. 2. Resources and circularity, promoting circular economy approaches in building materials and reducing construction waste. 3. Health, equity and resilience, ensuring buildings are sustainable, healthy, inclusive, and resilient to climate change. 4. Sustainable finance and ESG, channeling investments into green and responsible built environment solutions. They provide essential frameworks to guide governments, businesses, and organizations towards zero-carbon and climate-resilient buildings. With a network of over 75 national green building councils and tens of thousands of private members, World GBC can drive large-scale change globally. A wide range of standards and regulatory frameworks support sustainable building practices. At the European level, the Energy Performance of Buildings Directive is a key reference. National regulations, such as Spain's CTE and RIGHT, define the specific requirements for compliance. The Sustainable Development Goals also provide a global framework. International standards, like ISO 14040 and 14044 on life cycle assessment and ISO 21929 and 21931 on sustainability indicators in construction, help create comparable and reliable methodologies. Here you can access the main regulatory references related to the European and Spanish framework for building decarbonization. The Energy Performance of Buildings Directive (EPBD) sets the overall EU requirements for improving energy efficiency and reducing emissions in buildings. In Spain, these objectives are implemented through the RIGHT, Regulation on Thermal Installations in Buildings, and the CTE-DBHE, Energy Savings Basic Requirement, which define the national criteria for energy performance, renewable integration, and low-carbon building strategies. The Sustainable Development Goals, or SDGs, offer a shared global framework that guides countries, organizations, and industries toward a more sustainable and equitable future. They were adopted by all UN member states and outline 17 interconnected objectives that range from climate action and biodiversity protection to social well-being and economic development. For the building and construction sector, the SDGs are particularly relevant because they help us understand how our design and policy decisions contribute to broader societal outcomes. Goals such as clean energy, sustainable cities, responsible consumption, and climate action are directly influenced by how we plan, construct, operate, and renovate buildings. Green building certifications play an important role in guiding sustainable construction. They provide structured and internationally recognized frameworks that help evaluate a building's environmental and social performance. Instead of treating sustainability as an isolated step, these systems encourage project teams to integrate sustainable decisions from the very beginning of the design process, all the way through construction and operation. Among the many certification schemes available today, two of the most widely used worldwide are LEED and BREEAM. Both systems help project teams set clear sustainability goals and monitor their achievement across different categories. LEED, Leadership in Energy and Environmental Design, EAS, developed by the U.S. Green Building Council, has become one of the most globally recognized sustainability rating systems. It evaluates buildings across several performance categories, including energy efficiency, material use, indoor environmental quality, water management, and the impact the building has on the site and its surroundings. Projects earn points depending on how well they meet these criteria, and the final score determines the certification level: certified, silver, gold, or platinum. LEED is valued for its clarity and consistency, and it provides a practical framework for designing buildings that use energy more efficiently, support occupant comfort, and reduce environmental impact. BREEAM, Building Research Establishment Environmental Assessment Method, originally developed in the United Kingdom, is one of the longest established sustainability assessment methods. It covers a wide range of categories, from project management and energy performance to materials, waste, health and well-being, and ecological protection. One of BREEAM's strengths is its holistic approach, which encourages teams to consider the building's entire life cycle and its relationship with the surrounding environment. Buildings are rated on a scale from pass to outstanding, depending on their performance. In this module, we established the core principles behind green building and why they are essential for the future of the AECO sector. We began by examining the global challenges shaping today's built environment: climate change, resource depletion, and the increasing environmental pressures linked to construction and operation. These factors make sustainability a structural requirement rather than an optional practice. We then reviewed the regulatory landscape, from European directives to national requirements, and how these frameworks guide the transition toward nearly zero energy and zero emission buildings. In parallel, we looked at the contribution of international organizations such as the IPCC, the Global Alliance for Buildings and Construction, and the World Green Building Council, which provide guidance, data, and long-term visions for decarbonizing the sector. Finally, we explored leading certification systems such as LEED and BREEAM, which offer structured methodologies for evaluating and improving environmental performance across a building's entire life cycle. Together, these elements form a solid foundation that will support the more technical and material-focused topics we will address in the next modules. Before we finish, I want to briefly emphasize that the ideas introduced in this module are supported by well-established environmental standards and digital practices that guide sustainability within AECO workflows. In the next module, we will move from these foundations to a more technical focus on materials, learning how to characterize them and how to create a complete datasheet for use in BIM and simulation environments. Thank you for your participation. I look forward to seeing you in the next session.
Welcome to Module 2.1.2, Building Materials, Key Properties and Attributes. In this module, we will focus on the material characteristics that are essential for accurate simulation, digital modeling, and sustainable building management. Accurate material characterization is essential not only for design and construction, but also for digital models, simulations, and sustainability assessments. Many green building certifications require detailed documentation of materials, including environmental declarations, performance tests, and compliance certificates. This reinforces the importance of complete material characterization for achieving certification targets and demonstrating compliance. In digital building platforms such as BIM, materials are not just visual elements. They carry crucial information used for energy simulations, structural analysis, thermal comfort evaluation, and environmental impact assessment. Accurate and complete material data ensures that the digital model reflects real-world performance and supports informed decision-making. Without reliable material data, the digital model loses analytical value. Material properties are guided by international, regional, and local standards. International, ASHRAE Handbook, ISO 10456, Thermal Properties, ISO 14040/44 for LCA, and CN/TC 350 for Environmental Performance. Local/national, in Spain, UNE standards such as UNEN ISO 10456, UNEN 12524, UNEN ISO 6946, and UNEN 15804 provide guidance on thermal properties and environmental declarations. Guidance from professional bodies. CIBS in the UK offers practical recommendations for material properties in building design. Material properties are guided by a wide range of standards at international and national and regional levels. International references include the ASHRAE Handbook, ISO 10456 for thermal properties, ISO 14040 and 14044 for life cycle assessment, and the CEN technical committees related to thermal performance and sustainability. At national or local level, countries rely on their own regulatory frameworks. For example, in Spain there are the UNE standards and the CTE, Código Técnico de la Edificación. Also, there are some guides from professional bodies, such as CIBS in the UK, which offers practical recommendations for material properties in building design. It is important to note that access to these standards varies. Some documents are freely available, others offer partial public extracts, and many require purchase or institutional access. Throughout the next slides, we will indicate the most relevant sources and how to locate them. ASHRAE, the American Society of Heating, Refrigerating and Air Conditioning Engineers, is one of the most influential organizations in the field of building performance and HVAC engineering. It develops standards and guidelines widely used in HVAC design, building performance and energy modeling. For material properties, the ASHRAE Handbook is especially relevant, as it includes thermal and physical data used in simulations and design models. ASHRAE also develops different standards supporting energy calculations and environmental conditions. While most ASHRAE publications require purchase or membership, certain summaries or extracts can be accessed freely. ISO, International Organization for Standardization, is the main global developer creating harmonized standards across countries and industries, including construction, materials and sustainability. For our topic, ISO 10456 provides reference thermal properties for building materials, ISO 21929 and ISO 21931 about sustainability in building construction, and the ISO 14040 series outlines life cycle assessment methodology. ISO standards generally require purchase, though abstracts and overviews are freely accessible. CN, European Committee for Standardization, develops European standards that apply across EU member states. Two committees are especially relevant, CN/TC89, which focuses on thermal performance, and CN/TC350, dedicated to sustainability and environmental assessment. CN standards must be purchased through each country's national standardization body, such as ENER, in the case of Spain. The CTE is Spain's national building regulation. It defines required performance levels for safety, energy efficiency, and sustainability. The DBHE section is particularly relevant to materials because it references thermal performance and energy criteria. CTE documents are fully public and freely accessible online. UNE is the organization in charge of Spanish standardization. Many of its documents are national adaptations of ISO and European standards, including key references for material properties such as UNEN ISO 10456, about thermal properties of materials, UNEN 12524, about reference thermal properties, UNEN ISO 6946 about thermal resistance of building components, and UNEN 15804 about environmental product declarations, EPD. UNE standards are paid publications, but most include a free preview of the first pages. CIBS, Chartered Institution of Building Services Engineers, is the main professional institution for building services engineers in the UK. Its guides A and B are widely used for environmental design and HVAC performance and include useful material and comfort parameters. Most CIBS publications require purchase, although a limited selection is available in open access. Now that we have reviewed the regulatory context and the main organizations behind these standards, we can move on to the practical side. In the next section, we will outline the key categories of material properties required for building performance simulation. Material properties can be organized into several main categories. Thermal properties include conductivity, resistance, and heat capacity, which determine how a material responds to temperature changes. Mechanical properties cover strength, elasticity, and density, affecting structural performance and stability. Moisture-related properties such as absorption and permeability influence how materials interact with water and humidity. Environmental properties encompass factors like embodied carbon, recyclability, and environmental product declarations, which help assess sustainability. Finally, durability and maintenance properties describe the lifespan of materials and how they degrade under real-world conditions. Next, we present a glossary of the parameters needed to fully define a material within a BIM simulation environment. These parameters are organized into three main groups: general values, specific values, and life cycle assessment data. Let's start with general values. These are the basic parameters that describe a material's physical and thermal behavior. They include roughness, thickness, thermal conductivity, density, and specific heat. We also consider how materials interact with solar, visible, and infrared radiation, through absorptance, transmittance, and reflectance values, as well as emissivity. Additional parameters cover fire performance, indoor air quality, and special material types like gases or no-mass layers. Finally, properties like permeance, porosity, and temperature-dependent behavior are also part of the general dataset, providing the foundation for accurate simulations. Specific values refine the general data for a particular material or product. These include absorptance, reflectance, emittance, and transmittance, which describe how the material interacts with radiation. Thermal resistance, or R value, measures the ability to resist heat flow. Percent existing is used in renovation projects to indicate how much of a component is preserved. Permeability shows how easily fluids pass through the material. while heat capacity indicates the amount of heat the material can store. These parameters help make the simulation precise and tailored to the actual building components. The third group contains life cycle assessment data, which help evaluate the environmental impact of materials. Key parameters include recycled content, embodied carbon and energy, and various impact potentials such as global warming, ozone depletion, photochemical ozone creation, acidification, eutrophication, and resource depletion. Additionally, the emissions of gases like N2O, CO, and CO2 are recorded. Together, these LCA values allow us to assess the sustainability performance of materials in a BM model and support greener building design. Having a complete set of these properties allows for reliable energy modeling and environmental assessment. To fully exploit digital models, each material should have a datasheet that includes identification and product name, physical and mechanical properties, thermal and moisture properties, environmental impact and certification, e.g., EPD, references to standards and testing methods. A complete datasheet ensures compatibility with BM platforms and supports sustainability assessment workflows. In this module, we developed a clear understanding of why material properties are essential for reliable digital modeling and simulation. We began by examining the role of material documentation and how accurate characterization supports certification processes, performance assessment, and compliance with sustainability requirements. We then explored how BM platforms rely on material data not only for visualization, but also for energy analysis, thermal comfort evaluation, structural assessment, and environmental modeling. Without complete and reliable material information, these digital processes lose accuracy and analytical value. We also reviewed the main international and national standards that define material properties, from ASHRAE and ISO to CN, UNE, and guidance from professional bodies such as CIPS. These frameworks ensure that material data is consistent, comparable, and aligned with recognized methodologies. Finally, we walked through the different categories of properties required for simulation: thermal, mechanical, moisture-related, environmental, and durability, and how these inform the development of a complete technical datasheet. This datasheet is the foundation for integrating materials into BM models and for supporting performance evaluation. Together, these elements provide the technical and regulatory background needed to prepare materials for digital workflows and sustainability assessments. Before we close, I want to highlight that the material properties and standards discussed in this module form the technical foundation needed for accurate digital modeling and simulation. In the next module, we will move into life cycle assessment and explore how material characterization directly supports sustainability evaluation and whole-life environmental performance. Thank you for your participation. I look forward to seeing you in the next session.
Welcome to Module 2.1.3, where we will take our first structured look at building life cycle assessment, often referred to simply as LCA. In this session, our goal is to understand what LCA means in the context of buildings, why it matters, and which types of material data we need to make these assessments meaningful. We'll begin by outlining the main contents of this module, starting with the core concepts of building life cycle assessment and how environmental impacts are measured throughout the full life cycle of a building, from material extraction to end of life. Next, we will link building LCA with material characterization, highlighting why reliable material data is essential and how EPD documents support green labeling and certification. We will also introduce the main LCA material databases, including OCOBODAT, EPIC, and ICE, and briefly explain the type of information each one provides within the LCA workflow. Finally, we will present one-click LCA, giving you a high-level view of the platform, its main functions, and the types of reports it can generate for building projects. By the end of this introduction, you should have a clear understanding of how building LCA works, what information it depends on, and how digital tools and databases support the process. Let's begin. To start from a solid reference point, it is helpful to refer to the international standard that defines this method. According to ISO 14040, life cycle assessment is the compilation and evaluation of all the inputs, outputs, and potential environmental impacts of a product system throughout its life cycle. In simple terms, this means that LCA gives us a clear and structured way to understand how a product or building component affects the environment from beginning to end. We will look at the different life cycle stages in the next slide, so for now, the key idea is that LCA provides a systematic, comprehensive, and evidence-based approach. By following this international standard, we ensure that our assessments remain consistent, transparent, and aligned with best practices. This definition will guide the tools and methods we will explore throughout the course. To start from a solid reference point, building life cycle assessment builds on the structure provided by the ISO framework, but applies it specifically to buildings. Instead of looking at a single product, we consider the entire building as a complex product system, one that interacts with the environment over many decades. This broader perspective means that building LCA does not focus only on materials or construction. It also includes the long-term effects of use, energy consumption, maintenance, and what happens at the end of life. All these stages contribute to the building's overall environmental profile. Research in the field, including studies like Sharma et al., 2011, reinforces this whole building view by showing how impacts shift across different stages of the building's service life, especially when comparing construction to operation. Taken together, these elements help us understand building LCA as a systematic, long-term, and evidence-based approach for evaluating environmental performance across the full life of a building. This is the perspective we will follow throughout the course. Buildings behave very differently from most manufactured products. They are made of many interconnected components, they stay in service for several decades, and their operational energy use often becomes the main source of environmental impact. Because of this long lifespan and the complexity of their systems, we cannot understand a building's environmental performance by looking only at materials or construction. This is why building LCA needs a broader and more structured approach. It has to consider how materials, energy use, maintenance, renovation, and end-of-life processes interact over time. Only with this wider perspective can we capture the full environmental footprint of a building. The European standard EN 15978 provides the methodological backbone for developing a building LCA. It structures the assessment into distinct life cycle stages: the product stage, A1, A3, the construction stage, A4, A5, the use stage, B1, B7, the end-of-life stage, C1, C4, and the beyond the system stage, Module D. This staged structure is not only a way of organizing information, it directly shapes the scope, the boundaries, and ultimately the results of the LCA. Depending on which stages are included, excluded, or emphasized, the outcome can change significantly. This is why adhering to EN 15978 is essential for producing LCAs that are transparent, comparable, and methodologically consistent. In the following slides, we will look at each stage separately to understand how they fit into the overall workflow. The product stage, which includes modules A1 to A3, covers everything that takes place before materials reach the construction site. Module A1 refers to the extraction and preparation of raw materials, A2 covers the transport of these materials to the manufacturing facility, and A3 includes the manufacturing processes that transform them into construction products. This stage often carries a significant share of the upfront environmental impacts and sets the baseline for the rest of the building's life cycle. It is also the stage most commonly reported and analyzed by material manufacturers, since it forms the core of most LCA documentations. The construction stage, modules A4 and A5, begins once materials leave the factory. A4 includes their transport to the construction site, distance, vehicle type, and load efficiency matter here. A5 covers all on-site installation activities, including auxiliary materials, temporary works, waste generation, and energy used during construction. This stage highlights how logistics choices and site practices influence overall environmental performance. The usage stage covers all activities and resource demands that occur throughout the building's service life. Module B1 refers to general use, while B2 to B5 capture maintenance, repairs, replacement of components and refurbishment cycles. Modules B6 and B7 include operational energy and water use, which often dominate the long-term environmental impacts. Because this period can extend over several decades, the usage stage typically represents the largest share of a building's total footprint, especially in buildings with poor energy performance. At this point, energy models and energy performance simulations become essential, as they provide the data needed to estimate operational energy use and its associated carbon emissions. The end-of-life stage, which includes modules C1 to C4, begins when the building reaches the end of its service life. Module C1 covers deconstruction or demolition, C2 refers to the transport of materials to treatment facilities, C3 includes the sorting and processing of materials for recycling or recovery, and C4 accounts for final disposal. This stage highlights how material choices and design strategies can influence the building's footprint at the end of its life. When properly assessed, the end-of-life stage can lead to either a significant increase or a meaningful reduction in carbon impacts, depending on the potential for reuse, recycling and efficient waste management. Beyond the system boundary, Module D sits outside the main life cycle boundary, but it captures important benefits that occur after the building reaches the end of its service life. It considers scenarios where materials are reused, recycled, or recovered in other systems, reducing the need for new products and avoiding environmental burdens elsewhere. This stage is especially relevant because it is often where the largest carbon reductions can be achieved for many materials. A proper assessment of Module D helps reveal meaningful opportunities for circularity and shows how thoughtful design and material choices can generate positive impacts far beyond the building itself. Before we look at each boundary in detail, it's important to understand why these concepts exist. In life cycle assessment, system boundaries determine how much of the product's life cycle we choose to evaluate. Identifying these boundaries is a core methodological step because it defines which impacts are included, which are excluded, and how the results will ultimately be interpreted. These three terms, cradle to gate, cradle to grave, and cradle to cradle, represent different system boundary approaches used in life cycle assessment. Historically, most carbon footprint studies focused on cradle to gate, assessing only the impacts up to the point where a product leaves the factory. As LCA methodologies expanded, the industry moved toward cradle to grave, which considers the full life cycle including use and end-of-life phases. Today, the emerging trend is cradle to cradle, a circularity-based approach that evaluates how materials can re-enter future cycles through reuse, recovery, or recycling. Cradle to gate evaluates the environmental impacts of a product from resource extraction, through transport, to manufacturing, ending at the moment the product leaves the factory. It does not include use, maintenance, demolition, or disposal. This boundary was widely used in early carbon footprint analyses because it is easier to quantify and relies primarily on manufacturer data. While still useful for comparing materials at the production stage, cradle to gate often underestimates long-term impacts, especially in buildings, where operational energy and end-of-life processes are significant. Cradle to grave expands the system boundary to cover the entire life cycle of a product, from raw material extraction, through its use, maintenance, and eventual replacement, all the way to demolition and final disposal. In building LCA, this is the standard approach, because buildings remain in service for decades and generate substantial impacts during their operational phase. By capturing the full sequence of stages, cradle to grave provides a more accurate and comprehensive view of the building's environmental burden, supporting better long-term sustainability decisions. Cradle to cradle takes the assessment one step further. Rather than ending the analysis at disposal, it looks at how materials can re-enter new cycles as inputs for future products, whether through reuse, recycling, or energy recovery. This perspective is central to the circular economy, where materials are kept in circulation and retain value instead of becoming waste. Within the EN 15978 framework, cradle-to-cradle thinking aligns with Module D, which accounts for potential benefits beyond the system boundary. This approach is increasingly used in product design, sustainable construction, and material innovation, as it reduces resource consumption and supports long-term circularity. Let's introduce a key concept for this module: green labeling. Let's begin with a clear definition. Green labeling is the standardized practice of providing transparent and verified environmental information about products. Importantly, green labeling is not arbitrary, it is grounded in formal, internationally recognized standards. The ISO 14020 family establishes the overarching principles for environmental labels. ISO 14025 defines the rules for Type 3 environmental declarations, and EN 15804 sets the European core rules for environmental product declarations within the construction sector. To ensure credibility, this information must be verified by independent third parties. Organizations such as IBU in Germany, UL Environment in the United States, and BRE Global in the United Kingdom review and confirm that each declaration complies with the established standards. Together, this framework ensures that environmental data is transparent, comparable, and traceable, enabling reliable green labeling instruments such as eco-labels and detailed environmental product declarations, EPDs. To start this section, let me make it simple. Green labeling provides reliable lifecycle data that LCA practitioners and material developers depend on. For environmental assessment, these labels give verified and standardized data, in line with methodologies such as ISO 14040, ISO 14044, and the construction-specific standard EN 15804. Without these standards, we would not have consistent rules for measuring embodied carbon or for comparing products fairly. In practice, green labeling supports evidence-based decisions in early design, integrates with BIM workflows, and contributes to sustainability certifications such as LEED, BREEAM, and Levels. For industry and research, green labeling highlights environmental hotspots across the supply chain. This information helps manufacturers improve materials, optimize processes, and develop low-impact alternatives. Ultimately, green labeling turns environmental transparency into a key driver for better design, smarter decisions, and more sustainable buildings. Type 1 labels, defined by ISO 14024, are some of the most recognizable eco-labels on the market. In simple terms, Type 1 labels are third-party certifications awarded to products that meet predefined environmental criteria. They follow a checklist or threshold approach. A product either meets the criteria or it doesn't. These programs are managed by independent organizations such as the EU Eco-Label, Blue Angel, and Nordic Swan, and they consider environmental impacts from a lifecycle perspective, although they do not publish full numerical LCA results. Type 1 labels are very effective for consumer communication because they provide a clear and easy-to-interpret signal of environmental quality. However, for detailed LCA work, we usually need more granular data, which brings us to Type 3 labels. Type 2 labels, under ISO 14021, are self-declared environmental claims. The definition is, Type 2 labels are environmental statements made directly by manufacturers, without third-party verification. You have seen these countless times: recyclable, low VOC, biodegradable, contains 30% recycled content. Although they must follow ISO guidance to avoid misleading claims, they do not undergo external verification, which means their reliability can vary. These labels offer manufacturers flexibility in communication but require us, as designers, engineers, or LCA practitioners, to evaluate them critically. They can be useful for early screening, but they usually lack the rigor needed for scientific analysis or regulatory documentation. Type 3 labels are the most technical, and the most relevant for professional practice. In simple terms, Type 3 labels provide quantified, third-party verified environmental data based on a complete life cycle assessment. These are the environmental product declarations, or EPDs, used throughout the construction industry. They follow ISO 14025 and the construction-specific standard EN 15804, which ensure that all products are assessed under consistent and comparable rules. They also require independent verification and full compliance with product category rules, or PCRs. EPDs present detailed numerical results across the lifecycle modules A1 to C4, as well as the optional module D. Because of this structure, EPDs play a central role in building-level lifecycle assessments, in BIM to LCA workflows, in embodied carbon accounting, and in sustainability certifications such as LEED and BREEAM. So, if Type 1 labels help guide consumers, and Type 2 labels communicate marketing claims, Type 3 labels provide the scientific data we need for accurate and reliable environmental assessment. Now that we understand the broader category of Type 3 labels, let's focus on what an Environmental Product Declaration, or EPD, provides in practice. An EPD is essentially a structured summary of a product's lifecycle impacts. It condenses a full lifecycle assessment into a format that is clear, comparable, and ready to use in building analysis. For building performance evaluations, EPDs are especially important because they deliver the numerical environmental impact values that we need for accurate embodied carbon calculations. These values feed directly into building-level LCA and support BIM to LCA integrations, where material choices are assessed based on real, verified data. EPDs also play a key role in material development. By showing where the most significant impacts occur, they help manufacturers identify environmental hotspots, optimize production processes, and drive innovation in lower-impact materials. In short, the EPD transforms detailed LCA results into actionable information that benefits both design teams and material developers, improving the overall quality and sustainability of building projects. On this slide, we shift our attention to how an EPD organizes environmental information, rather than revisiting the lifecycle stages themselves, which we have already covered. EPDs use the modular structure defined by EN 15804, meaning that all impact results are presented within a common set of modules. This includes the A, B, and C modules, along with the optional module D, which captures benefits beyond the system boundary. The strength of this structure is that it makes the environmental data consistent, transparent, and directly comparable across different products and suppliers. It also helps us quickly identify which stages of the life cycle contribute most to a material's environmental burden. For building-level assessments, this modular arrangement is especially valuable because it integrates smoothly with LCA tools. The modules reported in the EPD align with the data required for whole building calculations, ensuring accuracy and coherence throughout the analysis. On this slide, we review the formal process for creating an environmental product declaration, following ISO standards. First, the process begins with the Product Category Rule, or PCR. This document sets the framework. It defines what data must be included, how each impact should be measured, and where the system boundaries lie for a specific product type. Without a PCR, it is not possible to develop a compliant EPD. Second, the manufacturer conducts a lifecycle assessment, following ISO 14040 and 14044 and strictly aligned with the PCR. This LCA is the technical foundation of the EPD, providing a comprehensive assessment of resource use, emissions, and environmental impacts from raw material extraction through the specified lifecycle stages. Third, the LCA results are compiled into the EPD document. Here, the information is distilled into a standardized and transparent format. The focus is on accuracy, clarity, and avoiding any marketing claims, ensuring the document reflects only verified environmental data. Fourth, the EPD undergoes independent third-party review and verification. A program operator examines the methodology, the data, and the final document to confirm compliance with ISO 14025 and the applicable PCR. Finally, after verification, the EPD is registered and published, making its environmental information available to architects, engineers, contractors, and certification programs such as LEED. This sequence of steps, which includes the PCR, the LCA, the compilation of the EPD, the independent verification, and the final registration, ensures that EPDs remain credible, consistent, and comparable across manufacturers. On this slide, we focus on the main environmental impact indicators reported in an EPD, along with the units in which they are expressed. We begin with global warming potential, reported in kilograms of CO2 equivalent. This indicator reflects how the product contributes to climate change and is one of the most referenced values in an EPD. Next is photochemical ozone creation potential, expressed in kilograms of ozone equivalent. This helps quantify the product's potential to contribute to smog formation. The third indicator is eutrophication potential, measured in kilograms of phosphate equivalent. It tells us how the product may influence nutrient accumulation in aquatic environments. And lastly, acidification potential, reported in kilograms of SO2 equivalent. This indicator reflects the potential for emissions to acidify soils and water bodies. Together, these indicators outline the product's broader environmental impact profile. Now let's look at resource-related indicators and their units. We start with primary energy demand, which is measured in megajoules. This value reflects the total energy used across the life cycle. Next is water consumption, expressed in cubic meters, capturing both direct and indirect water use in manufacturing processes. We then have non-renewable resource use, also measured in megajoules, representing the consumption of fossil fuels and other finite materials. Some EPDs may also include optional metrics, such as VOC emissions or third-party certifications, each with its own specific units depending on the testing method. These additional indicators expand the transparency provided by the EPD. Overall, these resource metrics complement the impact indicators by showing how the product interacts with energy and material resources throughout its life cycle. On this slide, we review how to interpret the environmental impact results in an EPD. The first block shows the impact categories: global warming potential, ozone depletion, acidification, eutrophication, and the abiotic depletion indicators. Each category represents a different type of environmental burden associated with the material. The second block focuses on the lifecycle module contributions. The table displays the percentage of each impact coming from stages like A1, A3, which often dominate due to raw material extraction and manufacturing. Other stages, such as transport or end of life, may contribute less but can still affect specific indicators. The final block uses a stacked bar chart to visually highlight which stages drive most of the environmental impact. This helps identify hotspots and guides where design or material improvements will have the greatest effect. By learning to read both the percentage table and the stacked bar chart, we gain a clear understanding of not only the magnitude of each impact, but also its distribution across the life cycle. This level of insight is essential for making informed and accurate environmental design decisions. On this slide, we examine the main sections typically found in an Environmental Product Declaration, EPD, using the Western Suburbs Concrete WN 5020 Premix Concrete document as an example. The first section is product information. This part provides a clear description of the product, its key materials and components, and an overview of the manufacturing process. It gives us essential context about what is being assessed and how it is produced. The second section is LCA scope and methodology. Here, the EPD outlines the functional unit, system boundaries, and the lifecycle modules included in the study. It also describes the data sources and assumptions used to carry out the assessment. The third section presents the environmental impact results. This is where we find indicators such as global warming potential, acidification, eutrophication, and others, along with resource use, energy demand, and the contribution of each lifecycle stage. These results are the technical core of the EPD and help us understand where the main environmental impacts occur. Beyond the core content, an EPD may include additional environmental information. Depending on the product category, this may cover aspects such as VOC emissions, optional test results, or other certifications relevant to the product. Another essential section is verification and standards compliance. Every third-party EPD must reference the governing standards, such as ISO 14025 and EN 15804, and it must identify the program operator and the independent verifier who confirm that the document meets those requirements. Finally, EPDs include administrative information, such as the manufacturer's details, the publication and expiration dates, and other data needed to ensure traceability. These sections together create a structured, transparent, and standardized document that allows designers, engineers, and researchers to interpret the environmental impacts of a material with confidence. Before we explore the specific platforms, it's important to clarify how access works. EPD databases are centralized digital repositories where we can find third-party verified environmental product declarations, all structured under ISO 14025 and EN 15804 to ensure transparency and comparability. Regarding access, there is no single model. Many EPD databases, especially those run by national or international program operators, are fully public and open access, allowing anyone to download the documents. Examples include IBU, Environdec, INES, and most national registries. However, some platforms integrate additional analytical tools, data processing, or external datasets. These may require a subscription or paid access, particularly in the case of commercial tools such as one-click LCA or EC3 professional features. This distinction is important because it determines how teams obtain data for building LCA, material benchmarking, and green certification workflows. In this slide, we explore the main categories of EPD databases and program operators. First, we have international EPD programs, such as the International EPD System, which manage globally recognized declarations under ISO and EN standards. Then, there are national or regional databases, like INES in France or Cobadat in Germany. These systems centralize EPDs that comply with local regulations and construction standards. We also find sector-specific repositories, focused on particular industries such as electrical equipment, wood products, or construction materials. Finally, emerging digital EPD platforms, such as EPD Global DG or the EPD Registry, offer structured and machine-readable data, enabling direct integration with BIM models and LCA software. These databases are particularly important for workflows that require automation and high data consistency. This slide focuses on the different types of EPD documents that manufacturers or industry groups can publish. The most common type is the product-specific EPD, which describes the environmental performance of a single, clearly defined product. Some operators allow multi-product EPDs, where similar products from the same manufacturer are grouped together when their environmental profiles are consistent. A sector average EPD represents the typical performance of a product category, based on aggregated data from several companies. It is useful when no product-specific EPD exists, but it provides lower precision. Another type is the trader or distributor EPD, issued by organizations that market the product but are not the manufacturer. Finally, some programs enable pre-market or prototype EPDs, allowing emerging products to be evaluated before entering full production. These documents help anticipate the environmental impact at early design or pre-commercialization stages. Let's look at the main types of EPDs, based on verification level. First, third-party verified EPDs. These are the most widely recognized. They are published by an official program operator and can be used for almost any purpose. They are valid for 5 years. If key parameters change, such as materials, manufacturing processes, or energy use, the EPD must be updated and possibly re-verified. Some operators offer variant EPDs, based on an existing third-party verified EPD, using similar materials and processes. All of these comply with the norms we discussed earlier. Next, project EPDs. These are created for specific projects or contracts. They are verified internally, rather than by a third party. Project EPDs help companies manage environmental impacts at the project level and are marked internally verified. They allow wider adoption of EPDs without the costs of external verification, while still complying with the relevant standards. Then, self-declared environmental claims. These are statements made by the company itself without third-party verification. They must be truthful, verifiable, and not misleading. Self-declared claims can be shared privately in reports, spreadsheets, or BIM plugins, supporting transparency in projects or tenders. Finally, system-verified EPDs. These are generated automatically by a verified system, rather than checked individually. The system itself is verified, which allows scalable generation of EPDs for large product portfolios. They are commonly used in construction products such as ready-mix concrete. However, the documents themselves are not individually verified, unlike third-party EPDs. In short, these four types, third-party, project, self-declared, and system-verified, offer different balances of credibility, cost, and scalability, depending on the use case. In a building LCA, we organize every component and process into the lifecycle stages defined by EN 15978. We model material replacements, maintenance requirements, and end-of-life processes such as deconstruction, transport, and disposal. An essential part of the assessment is Module B6, which captures the building's operational energy consumption. If we have access to real data, such as electricity or natural gas bills, this provides the most accurate basis. However, for most projects, especially in early design phases, real consumption data is not available. In those cases, we rely on a building energy simulation, using tools like Energy Plus, Design Builder, or other validated engines, to estimate heating, cooling, lighting, and equipment loads. By integrating those simulation results into the LCA, we ensure that the assessment reflects realistic operational impacts, even in the absence of utility bills. Finally, all results are typically expressed per square meter of floor area, allowing consistent comparison across design alternatives. With this slide, we begin the section on calculation tools for building LCA, starting with the platform most commonly used in building projects, One-Click LCA. One-Click LCA is a fully web-based tool, so it does not require any local installation, and its interface is intuitive and easy to master, even for architects and designers who are new to life cycle assessment. Because it is designed specifically for building LCA, the workflow aligns naturally with architectural practice. It offers strong BIM integration, connecting directly with Revit, IFC-based models, and Excel quantity takeoffs, which significantly reduces manual data entry. Another major advantage is its access to extensive EPD databases, allowing users to assign environmental data quickly and consistently. Finally, the platform automates EN 15978 calculations and provides outputs compatible with major sustainability certifications, including LEED, BREEAM, DGNB, and Levels. Altogether, One-Click LCA provides a streamlined and accessible environment for conducting building-focused lifecycle assessments. Next, we move on to SEMA Pro, which takes a very different approach compared to web-based tools like One-Click LCA. SEMA Pro is a desktop application, so it requires local installation and a more technical setup. It is also the most widely used and industry-validated LCA software worldwide, especially for product-level lifecycle assessment. Because it is not limited to buildings, SEMA Pro is used across manufacturing, materials science, industrial processes, and research institutions. The platform follows a process-based modeling structure, allowing users to map complex product systems with a high level of detail. This flexibility comes with a more technical interface, which means that specialized LCA knowledge is generally required to build models correctly. SEMA Pro supports a wide range of professional datasets, such as EcoInvent, AgriFootprint, or ELCD, and provides powerful capabilities for scenario analysis, sensitivity assessments, and customized system boundaries. In short, SEMA Pro is the reference tool for rigorous, detailed, and sector-validated LCA studies, especially when the analysis goes beyond buildings and into broader product systems. And finally, we have OpenLCA, an open-source platform that provides a flexible environment for lifecycle modeling. Although it requires installation, it is free to use and compatible with major databases, which makes it very attractive for universities, research groups, and organizations looking for transparency and customization. Its modular structure allows users to build detailed models, define custom indicators, and document methodological choices in a very clear way. It's a strong option for research-driven or exploratory LCA workflows. The second group of tools are BIM integrated workflows, which connect the design model directly to the lifecycle assessment. Plugins and internal tools such as Tally, Graphisoft Design LCA, or Autodesk Insight can automatically extract material quantities straight from the BIM model. This greatly reduces manual data entry, which is one of the main sources of inconsistencies in traditional LCA workflows. These tools also minimize errors in complex assemblies, because the quantities come directly from the model geometry rather than from separate spreadsheets or manual takeoffs. Additionally, IFC-based workflows enable LCA tools to read data from multiple BIM platforms, expanding interoperability beyond Revit. Overall, the key advantage is consistent alignment with the evolving design model. As the BIM model updates, the LCA updates with it. This improves both accuracy and efficiency throughout the assessment. Finally, we consider the tools used to model operational energy, which is reported in Module B6 of an LCA. When real utility bill data is unavailable, something very common in early design phases, we rely on energy simulation engines such as Energy Plus, Design Builder, or IESVE. These tools estimate heating, cooling, lighting, and equipment loads using validated building physics models. The simulation outputs can then be exported to the LCA platform and assigned directly to Module B6, ensuring that operational energy impacts are captured in a consistent and realistic way. This approach allows the LCA to reflect credible energy use scenarios, even long before the building is constructed or occupied. In this module, we will work with a real-world case study, derived from the paper Building Information Model, BIM, and Life Cycle Analysis Tools, a comparative study with specialized software for environmental performance of buildings, published in the Proceedings of BS 2025, IBPSA. The project is a 161 square meters single-family home located in Pamplona. We use this example to compare two structural alternatives, masonry and timber, and to explore how each influences the building's environmental performance. The simplicity of the building makes it ideal for teaching, but the study remains sufficiently comprehensive to illustrate the full workflow, from the BIM model through to the LCA results. To obtain meaningful results, each construction system was modeled with full material detail within the BIM environment. The masonry option incorporates reinforced concrete and ceramic materials, while the timber alternative includes glued laminated timber and OSB panels. By defining each layer with its correct physical and environmental properties, the BIM model becomes a reliable source of quantities, ensuring that the LCA results reflect the actual building design. For the case study, the authors applied the methodology and tools introduced throughout the course by comparing three complementary LCA workflows. The first is the theoretical reference, where impacts are calculated using BIM-derived quantities and EPD factors, processed through user-guided calculations in Excel. This manual approach provides a transparent baseline to validate the other methods. The second is the indirect flow, using one-click LCA. BIM data is transferred into the platform, and the software performs the lifecycle calculations while the user defines key inputs. This reflects a professional, widely adopted workflow in building LCA practice. The third is the direct flow, enabled by the Design LCA plugin in ArchiCAD, which automates quantity extraction and delivers immediate environmental feedback directly within the BIM environment. It is especially effective for early-stage design iterations. Together, these three workflows illustrate how the concepts covered in the course translate into practical, real-world LCA applications. Let's begin with the global warming potential, GWP, results for each construction system, which represents the overall performance overview. In the masonry alternative, all methods show that most emissions originate in the production stage, A1, A3, mainly due to concrete and ceramic materials. In the timber alternative, results show greater variability. This is driven by how each tool handles biogenic carbon storage and end-of-life assumptions, which significantly influence the final GWP. Overall trends are similar, but the absolute values and phase distribution differ across tools, highlighting the importance of understanding the modeling assumptions behind each result. At the level of building elements, the masonry assemblies produce consistent results across all methods, reinforcing their stability in terms of environmental performance. The timber assemblies, however, present larger discrepancies, largely due to differences in biogenic carbon accounting and the treatment of end-of-life scenarios. We also observed that one-click LCA included undisclosed emission factors not explicitly found in the EPD documentation, causing deviations from the theoretical reference. This underlines an essential lesson: always understand the background data, default assumptions, and database behavior of the tools being used. Material-level analysis shows that reinforced concrete, brick, and OSB panels are the main contributors to embodied emissions. Design LCA provides consistent material results, but its lack of phase-specific detail limits the ability to identify which stages generate the highest impacts. For educational purposes, however, it supports quick comparisons between materials. The theoretical model and one-click LCA offer greater granularity, which is crucial when optimizing material substitutions, analyzing hotspots, or designing impact reduction strategies. Additionally, the BIM-based tool demonstrated the usefulness of directly comparing the carbon footprint of each construction material, enabling clear, side-by-side material comparisons when exploring different material choices. This case study shows that LCA results are strongly influenced by three elements: biogenic carbon accounting, end-of-life assumptions, and the quality and completeness of EPD data. For material developers, this underscores the need for transparent, phase-specific information to ensure that their products are assessed consistently across different tools. For the construction sector, BIM-integrated LCA supports faster, early-stage decisions, helping designers identify where low-carbon materials can be adopted without disrupting the project. More detailed tools then highlight hotspots and guide improvements in both product performance and EPD documentation. An additional insight is that clearer data also benefits market differentiation. Products with robust and well-documented environmental profiles gain a competitive advantage as regulations and clients increasingly prioritize carbon performance. In short, accurate data and clear assumptions allow the industry to make more reliable comparisons and promote genuinely low-impact solutions. As we conclude this course, I want to highlight a few core principles that will support your work moving forward. First, approaching projects from a full lifecycle perspective allows us to identify where environmental impacts actually occur and where design decisions can be most effective. Second, the credibility of any assessment relies on robust data and transparent assumptions. Understanding the origin and structure of the information, whether from EPDs, databases, or BIM-derived quantities, is essential for interpreting results correctly. We also reinforced the importance of integrating LCA early in the design process. Early evaluations enable meaningful comparisons, support low-carbon material selection, and guide the project toward more sustainable outcomes without disrupting the workflow. Lastly, LCA should be viewed not only as an assessment requirement, but as a strategic design tool. When applied consistently, it informs decisions, strengthens environmental accountability, and contributes to the development of higher-performing buildings. These principles provide a solid foundation for incorporating life cycle assessment into professional practice in a clear, effective, and sustainable way. Before we finish, I want to briefly acknowledge the standards and tools that supported this course: ISO 14040, ISO 14044, EN 15804, and the LCA platforms integrated into BIM workflows. They provide the rigor and consistency needed for reliable environmental assessment. Thank you for your participation. I encourage you to continue with the upcoming Exploit 4 InnoMat training modules, where we will build on these foundations and explore advanced methods and innovative materials. I look forward to seeing you in the next sessions. Welcome to the closing segment of Course 2.1, Introduction to Digital Modeling of Construction Materials and Their Properties. In this brief session, we will revisit the main ideas explored throughout the module and connect them to the broader digitalization strategies that guide modern construction practice. During the course, we reviewed the sustainability imperatives that motivate digital modeling, including the need to evaluate both operational and embodied impacts. We examined the essential physical and environmental properties of construction materials, how these properties are characterized and standardized, and how they affect building performance in real contexts. We also looked at life cycle assessment and environmental product declarations, which provide structured and transparent representations of environmental impacts across a material's life cycle. This closing segment brings these concepts together and prepares you for the more advanced modeling topics covered in the next modules. Let us begin with a summary of the key conclusions. Let us review the main conclusions of Course 2.1. The first conclusion is that sustainability provides the context for digital modeling. Understanding environmental pressures and performance requirements is essential for choosing appropriate materials and evaluating their implications on the entire life cycle of buildings. Second, accurate material characterization is fundamental for any digital workflow. Thermal conductivity, density, heat capacity, vapor permeability, mechanical resistance, and environmental indicators all influence the accuracy and credibility of modeling outputs. Third, standards such as ISO 10456, EN 15804, ISO 14040, and ASHRAE guidelines establish common methodological foundations. They ensure that data used in modeling remains consistent, comparable, and traceable across projects and tools. Fourth, life cycle assessment and environmental product declarations allow practitioners to quantify environmental impacts systematically and transparently. They make it possible to evaluate construction products based on evidence rather than assumptions. Finally, integrating these datasets into BIM, BEM, and LCA workflows supports coordinated decision-making and reduces uncertainty. These concepts form the foundation upon which more advanced digital modeling approaches will build in the next modules. To continue expanding your understanding of digital modeling of construction materials, several types of resources may be useful. Publications from the World Green Building Council, Global ABC, and IPCC offer a clear view of the sustainability landscape and help contextualize the role of material impacts. Technical documents such as ISO 10456, ASHRAE handbooks, and European or national normative frameworks provide validated methodologies for determining material properties. For environmental assessment, ISO 14040 and 14044, as well as EN 15804, define the reference methods used to build life cycle assessments and environmental product declarations. Databases like COBODAT, INES, and the International EPD system contain verified product data that can be included in digital models. LCA tools such as One-Click LCA, CIMAPro, and OpenLCA are useful for exploring how environmental data integrates with design and modeling workflows. A complete list of references used in this course will be provided so that you can consult each source in detail. It is important to recognize how the content of this course connects to the broader objectives of Exploit 4 Inomat. The project focuses on accelerating innovation in advanced construction materials, and high-quality material data is at the center of that mission. The concepts introduced in Course 2.1 provide the foundation for building digital datasets, feeding simulation tools, and supporting performance and sustainability assessments. Understanding material behavior, characterization methods, and environmental evaluation is essential for integrating data into BIM, energy models, and LCA platforms. This knowledge also supports the interoperability and validation activities carried out within the Exploit 4 Inomat Open Innovation Test Bed, where material performance is tested, upscaled, and assessed using a combination of laboratory data and digital modeling tools. Course 2. 1 prepares you for the more advanced modeling approaches that follow, including multi-scale simulation, multi-physics modeling, and data-driven workflows. These upcoming modules rely directly on the concepts established here. Thank you for completing Course 2.1, Introduction to Digital Modeling of Construction Materials and Their Properties. We appreciate your attention and commitment throughout the module. We hope the course has given you a clear understanding of how material properties, sustainability frameworks, and evaluation methods form the basis for digital modeling. These concepts support accurate simulations, transparent environmental assessments, and consistent decision-making. As you move into the next modules of the Exploit 4 Inomat training pathway, you will see how these foundations support more advanced modeling techniques and integrated workflows. Thank you again for your participation, and we look forward to guiding you through the next stages of the program.